measurement button. I'm not going to do that for you. I'll draw the line somewhere. Okay, so then for part C, Luke sinks 30 centimeters into the snow before coming to rest. What's the average force the snow exerts on him? So he goes from here and he goes down a little bit, just 30 centimeters though, to state 4, where at state 4 his kinetic energy is 0. So you can really take the same states you had here. K3 is going to equal, let's see, K3 is right, 1/2 m v3 squared. Okay, that's the speed that you found here when you hit the snow, about 17. I'm just going to remember that when you square it, you get 300. Okay, and then when he gets brought to a stop by the snow, K4 is 0, and his change in gravitational potential energy is negative mg, and I'm going to call d the 30 centimeters. Okay, so I'm going to make that distance d. He sinks. D is the 30 centimeters he goes down. Okay, so, and then, let's see. And then there's work done by the snow, right? So change in Luke's kinetic energy is the work done by gravity plus the work done by the snow. And that's going to be equal to the negative delta UG plus work done by the snow. And so what we get is work done by the snow is delta UG plus delta K. Okay, so his kinetic energy goes down. Let's see. So work done by the snow is negative. Hang on. Is negative mgd, and then right. No, I'm sorry, that's not work done. That's the this is the change in kinetic energy. Sorry, not kinetic, potential energy. Man, I cannot talk. Okay, and then negative 1/2 m. Let's see, right, m v3 squared. Okay, so the work done by the snow is going to be equal to negative, and I'm going to collect the m, right? So Luke's mass times gd minus 1/2 v3 squared. Okay, so have I done this right? Yeah. Okay. So right, and then the average force the snow exerts on him, okay, is going to be equal to the work the snow exerts on him divided by the distance over which he went. Because what you're doing here, let me back up and say that what you're doing here is you're saying the work done by the snow is approximately equal to, we're assuming, or basically to find the average force, you take the constant, let me do this way, constant, the constant force work equation, right, and apply that. So since the snow is pushing up on him while he's moving down, this dot product is just going to be the negative of the scalars. So negative Fs times, and then his displacement delta R was d. So that's where I'm getting that from. And so what this gets for us is, let me, I'm going to go ahead and get rid of my part A work at least. And I'm going to grab these two things. No, I'm not. And grab this and move it up here. And wow, planning. Yeah. Okay, complete lack of planning. Okay, so I'm just going to take this and keep writing up here. Forget about moving it. Okay, so this goes to asterisk in a circle. That's a sad looking asterisk, but trust me. All right, asterisk in a circle, and we're going to get the average force the snow exerts, I guess I should say average, okay, equals negative work done by the snow over the distance Luke falls through the snow, which is, of course, already given. Okay, so we have negative WS, and WS is given here. So the average force exerted by the snow is going to be mgd, or m times gd minus 1/2 v3 squared, and this negative sign here is going to cancel against that one. Okay, so the average snow force is going to be the mgd divided by d will just be mg minus, right, 1/2 m, well, let's just go with 1/2 m v, dang it, v3 squared over d. I'm going sort of to excessive lengths to make this, yeah, whatever. Okay, so what you can get here is that this is just Luke's weight, right, which is 75 times g, which is 10, okay? You don't know the Hoth is the same as Earth. I know more about Hoth than you do. I promise you. All right, so 750 newtons for this term. And then for this term, well, can't do that in my head. Okay, so the 1/2, let's see, v squared with v3 squared was 300. So divided by 2 is 150. And then times Luke's mass of 75 is a number I cannot do in my head. So it's something. What you're going to find, wait a minute. Hold on. Ah, here we go. Okay, error, Dr. Smith. This I tried to simplify here, but that means this should have been positive because I was pulling out the negative sign. Okay, so now, there we go. That's more like it because it didn't seem right. Because see, what this was saying when the negative sign was here was, oh, the faster Luke's going, the less work the snow has to do. No, that can't be right. Okay, so let's see. v3 squared. So 0.5 times Luke's mass of 75 kilograms times 300 for v3 squared, and that's all divided by 0.3, which is the distance because of the snow in meters, and it's 37,500 meters. So 37,500 newtons. So, and that's plus. So, you arguably could have just neglected this change in gravitational potential energy here. It didn't matter much, right? Because the bulk of the force the snow exerted the bulk of the work done by the snow really went into killing his kinetic energy. Okay, so the total is going to be 38 to 50 newtons, which is a lot. If you want to calculate the acceleration Luke has dealing with that, in fact, I think I will. So 38250. Oops. So that's the net force on Luke from the snow, or well, that's the force the snow exerts, normal force in the snow. Divide that by Luke's mass, and you find that's 510 meters per second squared of acceleration, which means he feels 51 G's of acceleration. Now that's assuming, actually, let me take the exclamation point off. 51 G acceleration. Okay. And that is a 51, trust me. All right, 51. That's a little more like it. Now that's assuming Luke sort of is going at full speed and then goes through a 30 centimeter displacement before coming to rest. So basically, his center of mass, if you will, has to go, from here to here, and be at full speed here and then 0 speed here. Probably what he's more likely to do, what anyone would do in this situation, is you would keep your legs below you so that your legs first make contact with the snow when your center mass is up here, and then you'd start bending your legs as you go down, and that's why you're taught to drop and roll, basically to extend the distance over which you do all that work, which then results in a lower acceleration on you. It's easier on your body. I mean, it spreads the work out and gets a lower force acting on you. So just, good procedure not to smack into the ground quickly, but to sort of stretch it out as much as you can, in case you're ever trying to destroy a giant mechanical walking thing with a lightsaber. Just saying.